Okay, so all right. So let's start with traditional, standard way of modeling time preference. Now, the standard way of modeling time preference assumes that investor only cares about delays in payoff in terms of in some sort of interest gain or loss, right? Now in um, the interest rate could be varying, but so depend you might have different levels you want to consider, but basically it's kind of like a okay, this is how much you get, how much interest you get this year. So if I ask you to delay being paid, then you want me to compensate you for the loss in interest that you might be able to get. Is this realistic? So this would be a motivation in finance.
Okay, so this in the standard way in economics and finance to take into consideration future payoff is to discount the future by a constant fraction each time period. This is typically denoted with the symbol delta, which is called a discount factor. So the overall utility equals to the utility you get in this period plus the utility you get in next period multiplied by the discount factor delta plus delta square, the utility in the period after, and so on. Now this in this formulation, delta obviously have to be smaller than 1 and bigger than 0. Otherwise, it's going to explode, right? If it's bigger than 1, right? If it's bigger or equal to 1, then the sum could sum up to infinity, right? So the discount factor is typically between 0 and 1 to take into consideration that if I ask you to wait, you would want some compensation, right? You want some compensation. The discount factor is related to another similar concept called discount rate in the following way, right? So the discount delta equals to 1 over 1 plus r, with r being the discount rate. You can consider discount rate just like an interest rate, right? So you can see that the higher the interest rate, the lower the discount factor, right? So if you can get a lot of interest from the bank, then you will be less willing to delay receiving payment, right? Because you are losing more money from waiting. So discount factor, it would be going down with rising interest rate, right? So you can discount rate is, you can imagine that's just like the interest rate. This formulation is not just used in economics and finance. It's also used pretty much in any scientific field that involve temporal modeling. But for example, these days, when you train artificial intelligence like AlphaGo, they are basically also trained with exponential discounting in mind, because you need the AI to be able to look forward, right? It needs to be smart enough to realize that it might not get a reward in the immediate turn, right? You play this move, you're going to get a big reward sometime down the road. Whenever you need to model this sort of temporal interaction, future payoff, then you will need some discounting, right? And the standard pretty much anywhere would be to discount the future period by a constant amount every period. So this is basically universal way of modeling things. The issue with this model is that it's very hard to get a consistent estimate of what the discount factor should be for humans, right? I mean, for an AI, this is something you specified, so there's no problem in that. But when we try to estimate the discount factor from actual human behavior, you can see that the estimates starting from 1970s to 2000 seems to be all over the place, right? So in this table, each dot is one study. Each dot is one study. And there have been many studies to try to estimate the discount factor, and there seems to be no consistency. What you see here is from the range of 0 to 1. 0 means the individuals do not actually care about the future, because any future payoff is being multiplied by 0. Some studies seem to suggest that people don't actually care about the future. On the other hand, there are some studies that estimated that the discount factor is very close to 1, which means people are actually quite patient. People are actually quite patient. There are even some that have higher than 1, which means they are more than patient. Right? They're kind of like, yeah, totally, I don't want money today, give me tomorrow. And you know what? I'm going to pay you. I'm going to pay you to keep the money from me. Right? So there seems to be no consistency. And it's not a problem of lack of study. Now, if you go back to something like 1980s, right, maybe or 1970s, you say, well, the number of studies, there were too few studies, right? So maybe that's why you are having estimates that are not really precise. But even all the way to year 2000, you have a lot of studies and it's still all over the place. So here presents you with a problem. The models, it's very elegant, right? And it seems very reasonable that you discount each future period by a constant amount. Yet there seems to be no consistency in what the actual discount factor should be, right? Besides, it's kind of extreme to say people don't care about the future, right? It seems just weird to say people do not care about the future at all in some of these studies, right? And on the other hand, we also know, probably from personal experience, a lot of cases where people are impatient, right? So we basically need a better model. We need a better model. Now, the issue at hand can be very well illustrated if I ask you this hypothetical question. Let's just say I'm going to give you $100 at this moment, right? Let's just you trust me, right? I'm going to give you $100 at this moment. Now, suppose, right? So let's just like $100, let's just like that, right? And then suppose I can give you more. I'll give you money 2 weeks later, right? So you can either get the 100 now, or you can wait 2 weeks and you can get some additional amount if you want. How much more or less, how much more or less would you want for you to wait 2 weeks? So it's either $100 now or some additional amount in 2 weeks. How much more do you want? How much more? 50? 20? 20? 10? 20? 20. Okay, 20 seems to be pretty common. Actually, it's actually pretty common. The thing is, if you think about this, it's actually quite ridiculous that you want to trend it. Yeah, okay. So you're saying that if I give you like 10,000, then you're gonna want what? So if I give you 10,000, it's either $10,000 today or some additional amount in 2 weeks. You would want, how much would you actually prefer? How much would you want in order to wait? So I only need to give you $50 more for you to wait something like 2 weeks for $10,000. Right. So that's actually a good question that we should explore in a moment. Right. So let's say we get a median of 20 in class. Right. What's the discount factor? Right. What's the discount factor? So basically, $100 today equals to delta 120 in 2 weeks, right? So that's the delta for 2 weeks, which means delta equals to 100 over 120. That is something like what? 5/6, right? 100 divided by 120. That's 0.833, right? Okay. Now the thing is, in a standard model, you discount every period by a constant amount, which means that if you follow the standard exponential discounting model, right? The standard model is called exponential discounting, and if you follow that model, then if you want, you would have a discount factor of 0.833 for every 2 weeks, which means in 1 year, right? In 1 year, you would want 100 divided by 0.833 raised to the power 26, which is 11,567, right? So you see the problem you see the problem we're facing here, right? If you actually believe in the exponential discounting model, the model which we discount every future period by a constant amount, then if you extrapolate what people say they want in this short duration, then it would get ridiculous conclusion. So that's a problem with the model, not your behavior, because your behavior is very standard. It's very common. The model is problematic. In some sense, there is no reason why exponential discounting would be the way humans behave. It's not based on it's not based on psychology, it's not based on anything that we observe. It's mostly mathematical elegance, right? Because if you have for example, if you have a constant future stream of income, like every period you get $100, exponential discounting would become a geometric series, right? Which gives you a very easy way to calculate the sum, right? You know what? Like something like you get $100 now plus next, right? Plus next period you would value it at 100, but discount by delta, then and so on and so forth, right? And this is more than 1, right? So this you can sum up to equal to what? 100 over 1 plus delta? Is it? Is it 1 plus delta? No. 1 minus 100, 1 minus delta, right? Yeah, see? Right, so yeah, AR so that's like, let me make sure this is correct. Yeah, it's correct. So if delta is 1, that becomes infinity, right? That's right. So so the reason why we use exponential discounting is mostly because it's mathematically elegant, right? It's pretty. It's not grounded in any observation of actual human behavior, because once you think about actual human behavior like this, it's clearly doesn't make sense to say that you're going to have a constant discount factor every period, because I don't think anyone would actually tell me it takes $10,000 for you to wait 1 year, right, over $100, right? I mean, I would, like, so realistically, yeah, let's ask this question, right? If I ask you to actually wait, I either give you $100 now, or if you can get more money in 1 year, how much would you want? Yeah, another 100, right? Something like that, perhaps. Right? I mean, it's still ridiculously large compared to the interest rate you get from the bank, but at least it's not $10,000, right? So exponential discounting is problematic in that way. You cannot extrapolate like that. It doesn't make sense, right? Do we actually see like real examples where you get such high discount factors? Yes, in the form of payday loan, which is basic. Payday loan is a type of loan that's very common in Western world, in America. Not so common in Hong Kong. At least not that I'm aware of. Perhaps they also exist. It's just not as not as common. So the way payday loan work is this. It's a short-term loan, usually 2 weeks or less. Why? Well, because it's intended to pay back at payday. Therefore, the name. In the United States, the norm is that you get paid every 2 weeks, which is while it's in Hong Kong, you typically get paid monthly. So in US, you get paid bi-weekly. When I was a teaching assistant in the US, I get paid bi-weekly. So these loans are called payday loan because kind of like, okay, I'm out of money, so I take a loan, and when my paycheck comes, I'm going to pay back the loan on that day. These loans are typically offered by pawn shops. Why? Because a lot of people in America have no bank account, so they have to cash their paycheck in pawn shops. See that title, the biggest one. Checks cashed. Why? Because there are plenty of people without bank account, typically poor people with no bank account. I think it's not. It's much less like common in Hong Kong for people to not have a bank account at all. I think there's for a variety of reasons, like perhaps there's a minimum deposit requirement, perhaps because of the inconvenience of reaching a bank. Because in the U.S. you might have to drive. You have to drive to reach a bank. For so variety of reasons, or perhaps they simply have credit rating that is so bad that the bank aren't willing to open a bank account for them. For a variety of reasons, there are plenty of poor people with no bank account. The only way they can cash their paycheck is to go to pawn shop. And these are also the people who likely run out of money, so the pawn shop offer them essentially an advance. So yeah, you need money, we'll lend you money. When your paycheck comes, we'll cash your paycheck and you can repay your loan. These loans are extremely expensive, very high effective interest rate. For example, it's not uncommon to have 10% interest for a 2-week loan, which all of you seems to suggest you will happily take, right? You all indicate that you want 20% to wait for 2 weeks. So 10% interest seems like bargain. But if you work it out, then effectively that's like 1,000% interest annually. 1,000% interest annually. And if you add in fees and such and so on, you could actually go to 7,000%. What I mean, loan shark, right? Loan shark. This actually happens also in Hong Kong. So this observation that people seem to be willing to accept very high interest in order to get money now is real, right? It's not hypothetical. People actually do this, right? And the exponent and it poses a challenge to exponential discounting model, because exponential discounting model would imply that they would be willing to pay implausible large sum of money for a lot if you ask them to wait like a year. Okay. So there is something wrong here. Now, this is a I think everyone in the academia agree with the observation that the exponential discounting model is clearly inadequate. Right? It cannot explain behavior like this. So how do you actually provide an alternative model? Is not settled. It's not settled. Unlike, I mean, in this area, like prospect theory is relatively settled. People pretty much accept, like, yeah, like people value gains and losses. I think there's not a lot of controversy in there anymore. Like gain loss is something that it seems like people actually do, right? And I think the academia has by and large accepted it that this is important in some decisions, right? Not all decisions, since we still model a lot of things with simple, like with the simple utilities that we have always been using, but people do not find it that contestable, that in some cases gain and losses would actually be meaningful. But in the case of discounting, I don't think that there's widespread agreement on which model actually is correct. So, what do you think is happening?
Over different periods.
Right. So that's standard behavioral explanation. The standard behavioral explanation is there is actually varying discount rates in different periods, right? And it's obviously varying in a systematic way. But that's the standard behavioral explanation. But which is also the one that we're going to focus on in this course, since this is behavioral economics. So, but it's not the only explanation. In fact, you just point out evidence that varying discount rate might not be the whole story just now, right? Because now, when asked if we give you $100, now you want 120 in 2 weeks. But I give you $10,000 now, you might just want 10,050 in 2 weeks, right? This would tell you that it's more than just discount rates or discount factors. Right? What do you think is happening?
It also depends on the amount.
Yeah, so it seems like in your case, the amount you want to compensate for waiting doesn't actually scale proportionally with the amount of money involved, right? How would a model like that work? Because if it's a model of discount rates or discount factor, then you should scale up proportionally, right? So my short-term discount factor is 80%, right? So it doesn't matter if it's 100 or 10,000, it's proportional. But in your case, it's not proportional. How would a model of that work?
Your discount rate depends on the amount of money that is being looked at.
Right. So I mean, in economics jargon, in economic terms, what do you think what would you call that? Like, so in the extreme case, like I mean, your case is kind of a hybrid. So let's say in the extreme case. So no matter how much money is involved, if you ask me to wait for 2 weeks, I want $20. What would you call that in economics? So yeah, it's pretty close, absolute. But don't think about it as intertemporal, right? Let's think about it more like classical microeconomics.
In elasticity.
When someone asks for a amount of money that doesn't vary with the quantity of stuff in concern, that's what? What do you call that sum of? You can either say, well, it's kind of a lump sum. You need a sort of a lump sum payment. Or basically, you can say it's a fixed cost, right? There's a fixed cost of waiting. So that's an alternative model, right? So one proposal is you could have a varying discount factor, which is the standard behavioral explanation. But in your case, your behavior suggests that perhaps people have some sort of fixed cost of waiting. You want me to wait, then I want that much, right? I want $20. Okay? It doesn't matter if it's 10,000 or 100. I want $20 to wait, right? That's one possibility, and that possibility has been raised.
I mean, in my brain, it's more like if it's petty cash, I want sort of like 20, 50. But when it goes really big, it sort of seems like an investment. Then I apply investment rates
Right.
on what kind of return I'm
Okay.
expecting.
So another alternative explanation is it's about the magnitude. So when you ask me so is it big? Like that's actually something people want to consider, right? So this, for example, it's like when you compare 100 versus 2 weeks. 100 might seem not a lot of money, right? So 2 weeks delay is the primary concern in your mind. That's one possibility. But if I ask you, if we are talking about $10,000, then suddenly $10,000 becomes primary concern versus the 2 weeks, right? Because it's all about the magnitude, right? Now, if I ask you, if we go to $10,000 versus 10 years, now maybe 10 years will become the primary concern again. So you see, it's about the magnitude of the various parts of the question, that which one captures your attention the most, right? When duration of wait captures your attention the most, then you might want a very high compensation because, right, you think, oh, that's rare, that's such a long time, blah blah blah. But then if the amount of money involved is what primarily captures your attention, then it suddenly becomes like much more rational per se, right? It's kind of like $10,000, like yeah, it feels like I should you kind of start to think like an investor. $10,000, like how much would I want, like as an investment? That actually also has been raised as a possible explanation. The thing is, human behavior is messy, right? It doesn't really conform to the elegance of mathematical modeling. There's just so much weird behavior that maybe one model cannot explain everything. Right. So that's why it's not a settled question, I think. So it could be varying discount rates, varying discount factors. It could be fixed cost. It could be this thing about relative magnitude and attention. Right. All these have been proposed as possible reasons why people seem to exhibit such varying degrees of discounting, right? So, oops, sorry. Okay. The reason why you have fixed costs might be also because of transaction costs, right? So fixed cost is often the first reason you want to come think about. Miscalculation, highly unlikely. I think based on this is very simple task. I don't think it's really miscalculation. Yes. Now, in some cases, you also want to consider things like competition for limited resources. Like the reason why you want it now is because you don't think it's going to exist anymore in 2 weeks. Right? That's also possible. So, assuming that you can rule out all these possibilities, the standard explanation in behavioral economics, which as I have to emphasize, is not settled. Is that people is impatient, right? There's something special about having something now. Now is now. Future is future. So having something now has special value. This behavior is called present bias. Yes, present bias. And one way that we think that one reason why we think this is true is if you ask a question like this one, where instead of asking people to wait now, you ask them to wait in 10 years. Like say, okay, I can give you $100 in 10 years, or I can give you $120 in 10 years and 2 weeks. How many of you would actually want $100 in 10 years instead of in 10 years, 2 weeks? Pretty much no one, right? If I ask you to wait for 2 weeks after 10 years, then most people seem to be quite patient. And this is supported by the experimental evidence. empirical evidence. If you rearrange the data from the previous studies in according not the date of publication, but the time horizon you ask people to wait, then there seems to be a pattern. Is that if you ask them to wait, like if you ask them to wait now, they're very impatient, right? But the longer the horizon, then the more patient they seem to be. That's it. And there seems to be a pretty strong pattern here, right? People are impatient if you ask them to wait now.
One point represent one
Study. One study. 1 point represent one study. So this is kind of like meta-analysis, right? Looking at all the different studies. Right. So now the most prevalent explanation is that the discount factor exhibit a hyperbolic shape. Consequently, this is called hyperbolic discounting. Right? People's discount factor exhibits a hyperbolic shape. So it's called hyperbolic discounting. This is not very easy to work with, especially in discrete time. It works. I mean, the hyperbolic shape is just not very convenient. So in economics, we very often use an approximation called a beta delta discounting. Use a beta delta discounting, which looks like this. The overall utility equals to the utility now plus beta delta utility in the next period plus delta square utility in the next period, and so on. So the difference with exponential discounting is the additional beta term that applies to all future periods. Right? Basically discount all future periods relative to this period by an additional amount. Any two adjacent future periods is still governed by exponential discounting. Now, if you ignore this current period, just look at the future period. This is exponential discounting. So future versus future, exponential discounting. Future versus now, there's an additional discounting term beta. This is called a beta delta model, and it's common in economic modeling. It's mostly because it's convenient. It works very well in discrete time. Whereas for hyperbolic discounting, the raw hyperbolic discounting, it's just not as nice looking. Furthermore, I have to say that the hyperbolic discounting, the hyperbolic shape that we observe, is based on empirical observation, and there is actually been some evidence that I'm going to present you in a moment that suggests that perhaps this two-parameter model might actually be closer to how the human brain works than the actual hyperbolic shape, right? The actual hyperbolic shape is basically saying that in people's minds somehow they have sort of a smooth function of discount factor, right? And that takes on a particular mathematical shape, a mathematical formula. This seems to be simpler, like conceptually. Conceptually, this is saying that future versus future, it's just standard exponential discounting. Any future period versus the current period, there's an additional discount. So it's conceptually simpler. And there is some evidence that suggests this might actually be closer to how a human brain works, which I'll show you in a moment. So that's the beta delta model. So if beta equals to 1, then you just get the standard modeling, right? Just no discount, no additional discount of the future versus today. If beta equals to 1 is more than 1, the decision maker values the current period more than the difference between two future periods, right? Today is special. The thing is, today is special, right? When tomorrow comes, tomorrow becomes today. Then then tomorrow, tomorrow is special, right? So that leads to what we call time inconsistency. Is that in this model, the decision maker is time inconsistent because her preference change over time, right? So today I am unwilling to wait, but I'm willing to wait tomorrow, right? If you ask me, like I don't want to wait today, but I'm willing to wait tomorrow. But when tomorrow comes, you don't actually want to wait. So that's a change in preference. So it's kind of like, okay, yeah, I don't want to study today. I will study tomorrow. Guess what? When tomorrow comes, you know. So basically, what you get is procrastination. This procrastination is only possible in a time inconsistent model, right? In a standard exponential discounting, the decision maker is time consistent, so he never procrastinate, right? What you think is right thing to do, you do, right? So if you think it's optimal to study tomorrow, you actually will study tomorrow. That's the implication of exponential discounting. In fact, exponential discounting is the only discount model. That's the only discount model that would give you time consistency, right? Because you're discounting every future period by a constant amount, which is why it's consistent. Once you move away from this constant discount per period, once you move away from it in any way, then you get time inconsistency, right? So that's why I say exponential discounting is chosen because it's mathematically elegant. Right? It seems just the right thing to do. Oh, so here's an example. Let's say you have a student. He has a midterm in 3 days. He can either spread out the study over 2 days or cram everything in 1 day. Cramming is more costly because of the lower efficiency. So if you study over 2 days, then the cost per day is 1 per day. One. Cost per day is 1. If you study everything in 1 day, then the cost will be 2.4, right? Just to capture diminishing productivity, right? Okay. Spread over 2 days is better. I'm going to assume beta is 0.7, delta is 0.9, and utility in each period is 10 minus the cost of studying, right? Just as a demonstration of how this model works. Okay. All right, so how does this model work? Now, this model works by typically the calculation goes as follows. You start with considering what the individual would do, what the individual want to do far ahead of time, right? So let me give you a timeline, right? This is the midterm. You can decide to study in t equals to 1 or t equals to 2. And typically, there will be a t equals to 0 where you don't actually get to choose to do things. You just kind of like thinking about what you would prefer to do. This is typically used as the benchmark. Why? Well, the reason why we have a t equals 0 as a benchmark where you cannot actually do anything is that every decision is in the future relative to t equals to 0. That is why essentially we are using a time consistent choice, time consistent preference as a benchmark. Everything is still in the future. So what you think you're going to do in t equals to 0 would be a time consistent benchmark. And we take that as what you truly want. Okay. So in t equals 0, what would the individual prefer to do? So this model it's tedious in that you have to basically solve every single case and compare the payoff, right? So t equals 0, study in, so how do I write it in the, okay, I'll just write this way. Study in t equals to 1 only. Study in t equals 2 only. Study in t equals 1 and 2, right? So you have 3 possibilities, and you have to calculate the utility. There's just pretty much no way around it in this model. So what do you do? Okay, so study in period 1. Now remember, at this moment we are at t equals 0, so everything is in the future. So that's beta delta 10 minus 2.4 plus, so I should have a bracket here, delta square 10, right? That's what happens if you study in period 1 only. Similarly, if you study in period 2 only, then you get beta delta 10 plus delta square 10 minus 2.4. And finally, if you study in both periods, that's delta 10 minus 1 plus delta square 10 minus 1, right? Okay. So you can use your calculator, punch the numbers, and what you should get is, in the first case, is 10 times 0.81 plus 7.6 times 0.9, and then multiply by 0.7, that's 10.46. In the second case, it's going to be better actually. If you're going to study in only one period, you try to delay it as much as possible. So that's 7.6 times 0.81 plus 10 times 0.9 multiplied by 0.7. That's 10.61. The third case, which actually I set it up such that is the best, is 9. It's going to be 9 times 0.81 plus 9 times 0.9 multiplied by 0.7. That's 10.77, right? So in far ahead of time, when everything is in the future, so the individual is actually using exponential discounting, then he actually going to prefer studying in both periods. That's the rational thing to do. So supposingly, when period 1 comes, if you want to follow through with your plan, you should start studying. Now, in this case, you want to calculate, okay, as once again, study in t equals to 1 only, right? So once again, you have to do all the calculations. Studying in period and t equals to 1 only, that becomes beta. Oh, sorry, that becomes it's now, right? So if you study in t equals to 1 only, that's 10 minus 2.4 this period plus beta delta 10 in the next period because there's no studying. Study in t equals to 2 only. That's better because no studying today plus beta delta 10 minus 2.4 tomorrow. Study in t equals to 1 and 2. That means studying in both days. That's 10 minus 1. Plus beta delta 10 minus 1. Right? So that's you can see that once you are in period 1, the period 1 payoff is no longer subject to beta, right? So if you calculate the values now, so actually I should leave myself with more space. Okay, so that's 7.6 plus 0.7 times 0. Oops. Okay, let's try again. 7.6 plus 0.7 times 0.9 times 10. That's 13.9 for the first for studying in period. Oh, let's use it right. Okay. Right. So that's 13.9. Studying in period 2 only, that's 10 plus 0.7 times 0.9 times 7.6. That's 14.79. And studying in the both periods would give you 9 plus 0.7 times 0.9 times 9, which is 14.67, which is, so now you have a preference reversal. Okay, so that's how the model works. When a period is in the future, it's subject to the discounting of beta. When that period becomes today, it's no longer subject to beta, so it suddenly becomes much more important. And as a result, while you might want to spread your study over 2 periods, when they are both in the future, when the first period actually arrives, it becomes today. You don't work. You find today particularly important versus the future. So you don't want to study today. You want to delay everything in the future. So that's the change in preference, right? So people change their mind. So who came up with this idea? It actually, the idea, the economists have been puzzled over people seems to have reversed, people seems to be inconsistent in time preference, at least as early as the 1950s. So this topic of time inconsistency usually attributed to a paper by Stokes in 1955. So that's kind of usually what people think is the earliest paper. But the way of modeling comes much later, right? So people raise the issue. There's not very consistent effort in trying to model it. People have think about it. For example, George Akerlof who won the Nobel Prize for Lennon's model. He also thought about it. Like he has this example where he had like another economist asked him to mail a box of stuff, asked him to mail a box of stuff, and Akerlof was saying, yeah, every morning when I wake up, I tell myself I'm going to do it, right? And then at the end of the day, every day I'm going to tell myself I'm going to do it tomorrow. So and he never managed to mail that box, right? So so people have thought about this problem, right? And in this model, you get such delay. You get such delay. In this case, the model is short enough that we are basically by the second period, I assume that you have to study. So the model that's done. What if you have a model much longer, like you have really many periods? The problem with that is computation, right? Computation is going to be a problem because in the way we are solving it, we are actually solving every single case, which is not possible if you actually have too many periods, right? So in this course, we focus on having only a few periods, like at most 3 or 4. That's still manageable. If you have too many periods, then you cannot actually solve it this way, and you have to resort to some other ways, perhaps prove things theoretically, or do simulations. Right? Okay. So that's the idea. that's the idea. When everything is in the future, everything is subject to beta, right? So tomorrow and the day after are subject to exponential discounting. They're both discounted by, because they're both inside the bracket discounted by beta. But when tomorrow comes, tomorrow becomes today. So the payoff is now outside of beta. It's not discounted by beta, whereas the day after is still discounted by beta. So their relative importance has changed. So in the beta delta model, you can actually make a distinction between decision maker that is aware of her time inconsistency, which we call these decision makers sophisticated. And if the decision maker is not aware of her time inconsistency, she is naive, right? So that's actually come much a few years later than the original beta delta model. The original beta delta model, the mathematical formulation actually came quite early in the 70s, 68 or 70, like it's pretty early, but it's not used to describe time preference. The formulation exists, but it's not used to describe time preference. The first time it was used to describe time preference is probably in 1994 by actually is in a dissertation by a now famous Harvard professor, David Leibson. So David Leibson wrote this paper, which used this old existing formulation to describe time preference in 1994. Right. So but in that model, he made no distinction between people who are aware versus not aware their time inconsistency. Then in 1999, there are two professors in UC Berkeley. They wrote this. They kind of work on the model, and they consider the implication of knowing versus not knowing your time consistency. Now, this basically has to do if you have learned game theory, for example, about what you think is going to happen in the future, your belief about what's going to happen in the future, right? You could have incorrect belief, right, about what's going to happen in the future. That would be the case of naive person. Like he thinks that he is going to be consistent in the future, which is incorrect. For a sophisticated person, then she actually understands that she is inconsistent. So she would actually use backward induction, essentially. She would use backward induction to foresee what's happening in the future. And she would eliminate options that is actually not credible. Right? So this would require backward induction. But if you remember from game theory, backward induction could take a lot of time. If the game is very complicated, exploring every possibility would take a long time. So by adding in the concept of sophistication, you add in a lot of computations. But in our case, what you need to do is actually just look back at the calculations, and we know, right? Where we know in t equals to 1, right? Studying in t equals to 1 only, studying in t equals to 2 only, and studying in t equals to 1 and 2, we know that now the rational option is the third one, which gives you 14.467. We know that the middle option, procrastination, is actually the one that would be carried out. So now, if you are sophisticated, that is, you actually understand your future behavior, then at period t equals 0, you look at what happens in period, you would actually predict in p equals to 1, you would make the choice of procrastination. So that means that studying in both periods is actually not a credible option because you know it's not going to be carried out in t equals to 1. That means that back in t equals to 1, when facing the various option, right? Right, when facing various option, while the utility of the third option is the highest, the sophisticated decision maker would know that that is not actually a possible choice. It won't work. It won't work. It's not going to be carried out. So she's going to eliminate that from a choice set, and as a result, as a result, did I copy the number wrong? Yeah, okay, that's correct. Okay, as a result, right? She would act. Okay. Oh, wait. In this case, there's actually no point of commitment, because with the remaining two choice, delaying is still the better choice. Why is that the case? Because I'm asking about commitment. Okay, that's why. Sorry. All right. So, okay. So she understands that she's actually not going to choose the second one. Now, if there is no way for her to commit herself, like she has to just do what make a decision every single period, then she understands that what would happen is that she's going to delay until day 2, and there's nothing she can do about it. Now, so there seems to be a sense of inevitability here. But in practice, people do have ways to commit themselves, right? Like you can have. How do you commit yourself to studying? Yeah, find a study partner. I think that's a good example, right? In my studying with someone else does not necessarily improve your efficiency in studying, but it's a very good commitment device, right? We all agree to study together, even though we might just be studying individually, right? I think people do that actually. You meet up to study together, but you might be studying different subjects. But that means that it's completely a commitment device, right? You're just committing to come together to study so that you would start early. So the use of commitment device does not make sense when you have exponential discounting, because exponential discounting is time consistent. If you think it's worthwhile to do, you do. There's no need for commitment. Commitment only makes sense if you have time inconsistency, right? So the fact that we observe people use commitment means that their preference must be time inconsistent in some way, right? So in this case, if you left to her own device without any commitment, then there's nothing she can do. But with commitment, if you give her set up a study group, or perhaps I don't know, there could be more extreme methods, in uninstalling games on your computers or cell phone or smartphones, right? Various ways of committing yourself. Then the individual would actually want to do that. So what now? So here, so the part of the reason why time inconsistent models becomes interesting to people studying economics is that it can explain commitment behavior. Now, the thing is, how common do you think commitment? How common do you think people actually use commitment? I think in the case of studying, it's a pretty obvious example. I think study group has a large commitment component. But outside of that, how often do you think people commit themselves? It's actually not that easy, I think. I mean, you can think of examples like alarm clock is kind of a commitment, perhaps, right, to wake up. But I'm not sure that you would want to use this model, use a discounting model to think about sleeping, right? I think it's more like you sleeping, you just pass out, right? So you need an alarm. Can you think of anything else that actually actually shows people routinely use commitment?
I mean, what other things are we talking about?
Anything, right? Anything where you think people might procrastinate or otherwise spend more time than they want. Then so they want to commit themselves not to do that. Right? Studying is one case. You think that you're going to just procrastinate, so you commit yourself to start studying early. This, I think, is a clear example. But can you think of any other examples?
I use bets. If I can't do something, I'm gonna buy my friend a drink. So in order not to buy my friend a drink, I have to finish it.
That's very rational. That's actually very rational. There's actually a website for that. There's actually a website for that.
I heard there's like an alarm clock. You have to pick like one of the organization you hate.
Right. So here's an interesting application: is Hong Kong. Now, in year 2011, for the Hong Kong government decided that it's going to give every adult permanent resident $6,000, a one-time stimulus measure. Now, Macau has been doing that for a long time, right? Macau does that every single year. Hong Kong, we have done it only once. And we are going to do it, we are sort of doing it again this year, but in a much more messy way, right? So, but the one in 2011 is truly universal. As long as you are an adult permanent resident, you are eligible to receive the $6,000. You don't even need to be in Hong Kong at the time of the policy, right? You can be a permanent resident who have already immigrated, right? And you can still apply, right? So 6,000 cash transfer through banks, right? You have to sign up, and then the government is going to wire money to you. Now, for economists, one very interesting feature is that there's a choice of receiving an additional $200 by delaying your application by 6 months, right? There's this option. Now, this option is the government said it offered this option for administrative reason. It wants to spread out the applications, right? So it offered this choice. What's the effective interest rate here? You get 200 out of 6,000 for waiting 6 months. Yeah, so that's what 3.33%, right? Yeah, right. 3.33% for 6 months. So that's basically like something like 6.67% in a year, right? Which is not bad. At the minimum, I don't think you can find any certified deposit that gives you such return, right? 6.67%, no way, right? So it's actually, if you look at this from the perspective of an investment, it's actually a really good deal, right? 6.67% interest rate. So there's a student, I think it's a final year student. He took this course. This is actually the first year I offered this course in CHK. So basically he ran a questionnaire, obviously non-incentivized, sample size 60, basically his class 59, basically his classmates, and he asked these 3 questions. How much bonus is needed for delaying the receipt of 6,000 for 6 months? How much do you want for waiting 12 months? How much do you want for waiting 24 months? Right? So it's just very simple. 3 questions. How much do you want? in order if I ask you to wait. So what did he find? Now the reason why you can estimate beta is because you have 3 data points. You have 6,000 today, that equals to beta delta for 6 months. Beta delta for 6 months, and that's going to be something like 6,000 plus x, right? 6 months, and then you have 6,000 equals to beta delta square 6,000 plus x 12 month, and then you have 6,000 equals to beta delta to power 4 times 6,000 plus x 24 months, right? So you have 3 data points, you have 2 parameters, you can estimate that. You can estimate the 2 parameters, right? It's actually a very simple exercise. It's just a simple non-linearly square, I think, right? You can do that in theta in one line, right? It's very simple. So the estimated beta is somewhere around 0.93, right? 0.93. So there's some present biasness, right? People generally find the current period a bit special on average, but you do see some people who have what we call future bias. Like they're actually so patient that it seems like they would be willing to pay money to wait, right? So but the average is slightly present bias. Monthly delta, nothing special here actually. You can see that the range is actually very small, right? The range here is actually quite small, nothing really special. So that's actually mean that the data is quite plausible. Typically, delta is very close to 1. Like 0.99 is actually quite common. Now, if you compare the delta with the 200 postponing reward, right? So so you can do some calculations, right? You can do some calculations, calculate the discount factor for a year. The discount factor for a year is 0.8666. So you can now, as I have said, the discount factor is related to the discount rate in the following equation. You can imagine this is just a discount. This is the interest rate required for you to wait. So the estimated annual discount rate is actually 15%. So people say, based on the answer people give you, based on the answer people gave, they seem to want annual interest rate of basically 15%. Right? If you want me to wait 1 year, you have to give me 15%. Right? This 6 months discount rate will be basically half of that, which is 7.5%. So since the actual reward for waiting is only 3.33%, you can expect very few people would wait, and that's actually the case. Not a lot of people actually wait. Now, for my part, I managed to convince my whole family to wait. Right? I mean, I can't accept being an economist, and particularly a behavioral economist. I can't accept not waiting. Dude, that's it's actually not hard to convince people. Once you ask them, so do you have money in the bank? Do you have money in certified deposit? Typically, if at least for people of my parents' age, they would almost always have money in certified deposit. Then you explain to them, look, that's a 6.7% interest rate, right? You don't think the Hong Kong government is going to default, right? So it's basically 6.7% interest on certified deposit. There's nowhere you can get that rate, right? So the rational thing to do is to just delay the $6,000, get the $200. If you need money, go get it from your bank, right? It's actually not hard to convince people if you want to explain the logic to them, right? Because how likely would someone not have $6,000 in their bank, right? It's very unlikely. But the thing is, if you don't explain it to people, most people's intuitive reaction would be to just get the money as soon as possible, right? So this is where I think it's actually irrational. right? I don't think it's actually irrational to have time inconsistent preference. I mean, it's just people could have time inconsistent preference. That's just the way we are born, perhaps. The thing is, why you want to get the $6,000 immediately? Why you keeping money in your bank? That's totally irrational, right? It's totally irrational. You should spend the money in your bank first, and then get them, and then leave the money with the government and earn the extra interest. Right? So this is what I think is irrational. All right. So here, now I'm going to start talking about the paper by Thaler. This is by far the most famous study on commitment usage. Thaler and Benazzi save more tomorrow. Use behavioral economics to increase employee savings. Journal of Political Economy. So this now the background. People do not save enough for retirement. This is a fact. Anywhere, people do not save enough for retirement. The only exception is when people actually have pensions. Then you have enough because you are not making the decision to save, right? You can either say you're being forced to save, or you can say someone else is saving for you, your employer. But these in modern times, retirement benefits has more or less switched from a pension system to what we call a defined contribution system. MPF is a defined contribution system. Defined contribution because your employer and you pay pay a certain amount to your savings or retirement savings account, and when you retire, that's the pot of money you have. That's the pot of money you have. Whereas for a pension, you typically draw from a pension until you die, right? There is no set limit on how much money you can actually draw. Theoretically, if you live forever, then you can keep drawing from a pension, right? So in modern times, people have pretty much a lot of people, including pretty much anyone, including anyone young enough in Hong Kong, would be on a defined contribution system where you have a fixed pot of money in the end, right? MPF is a fixed defined contribution program. And in these programs, people do not save enough. Think about it, right? The cap of mandatory contribution in MPF is 2,500 from yourself and 2,500 from your employer. That's 5,000 a month. You're saving $5,000 a month, right? I think it's 5,000, right? So is it even that much? Or is it 2,500 in total? Maybe it's actually 2,500 in total. I don't think it's 5,000 in total, because if it's 5,000 in total, then 1 year is already 60,000. I don't think it's actually that much. I think it's actually 2,500 in total. Yeah, that's $30,000 a year. So you're saving $30,000 a year maximum, right? So it's actually not a lot. It's actually not a lot. And in many other countries, it's even worse. Sometimes people simply have no retirement savings, right? So how do you encourage people to save more? The thing is, now if you're in the camp where you believe people are rational, you could just say, well, there's no need, right? There's no need. If people are time consistent, if they want to save, they can save. If they don't want to save, that means that they don't want to save, right? So if you believe in a time consistent model, there's nothing to say anymore. Just no need to force anyone to save. The fact that most countries force people to save implies that most governments and most voters believe that people are time inconsistent, right? So this study, Thaler managed to convince Philips Electronics to run an experiment with people's actual retirement saving. Now, what they do is this. This is an experiment. So you have a control group and a treatment group, and the control group and treatment group come from different departments. So in department, in department A, you go to department A is the control, and what they do is that in department A, you just give information about the importance of saving for your retirement, right? Just give them a pamphlet, right? Giving them a pamphlet explaining that it's important to save your retirement. That's it, right? In the case of the treatment group, what you offer them is the option to commit yourself to increase your savings automatically by a few percentage points starting from next year, right? So it's not like saying starting right now. It's like, okay, when you're when next year comes, right? When next year comes, do you want to save more, right? And you can commit yourself to doing that. Basically, if you say yes, I want to save more next year, then the company would automatically increase your contribution to your retirement account next year, right? So you commit yourself. The increase you can commit to increasing a certain amount each year, and the amount will stop when the savings rate reaches 10%, because saving 10% of the income for retirement seems pretty high, right? Okay. So what do they see? All right. So how do you interpret the results? So here are this is the table 4 is the most important table in this paper. It shows you all the results essentially. Now the program is called Save More Tomorrow, and it's shortened to SMART, right? I don't know how you get SMART out of Save More Tomorrow, but anyway, the program is called SMART.
I think it's SMTAL, so ignore it. So SMTAL is in the middle.
In the middle, yeah. But how do you get AR?
They ignore it. It's SMART.
All right. Okay.
SM and
yeah. Okay. Yeah. So in any case, yeah. So right. So the table is actually pretty big. So first, you have two groups of people here. You can see there are two columns. There's some people who are already saving for their retirement. There are actually some people who are not saving for their retirement, right? So there are actually people who were not saving for their retirement. Okay. So that's two group of people. Control group. Remember, these are people you just give them a pamphlet and say, hey, it's important to, you know what, it's important to save your retirement, right? So just kind of some information. There are a lot of people because giving them a pamphlet is very cheap, right? So the control group is large. Control group has almost 15,000 people in it, right? Just give them pamphlets. All right. So what you want to look at is how effective a plan, just an informational campaign will do, right? Just giving them information about how important it is to save your retirement. There is some effect, very tiny, like it raises their savings rate from 5.65% perhaps to 5.76%, like 0.1% effect, right? Very tiny effect on people's savings rate. For people who had not been saving at all, it's slightly more effective, 0.7%, but that's not really a meaningful change, right? Just saving about less than 1% more per year. Right? So, okay. So now, test group. This is the treatment, right? The treatment. There are two divisions that are involved, right? The two divisions. Just look at the combined version, like two divisions involved. These people are the ones who have the option of actually committing themselves to saving more starting from like next year. How many people actually join? The people who join is actually a minority, right? Now, for example, of the people who have been saving before this experiment, you have about 1 to 2, right? So for every 3 people, maybe 1 would join this program, 2 would not join, right? For people who have not been saving at all, it's much worse, right? It's almost 1 to 8, right? So every 9 people, 1 would be joining and 8 would not be joining, right? Which this by itself is actually a bit disheartening because these are the people who actually need this program, right? The people who have not been saving for their retirement. These are the people who actually want them to join. but actually they are very unlikely to join. You can't force. You can't force people to join this kind of experiment, right? So, but among the people who join, does it work? Well, it does. The strongest effect actually comes from people who have not been saving, but they joined this program. They raised their savings rate from 0 to 5%. Enormous effect, right? Going from nothing to 5%. So this is the biggest result. Really effective if people join. If you have been saving, this program is still slightly effective. It raises your savings rate by about 1.5%, right? 1.5%. Right? Because these people have already been saving over 5%, right? So they slightly increase it to 6.8%. So there's still some effect. Furthermore, there's spillover effect. Because you see, well, okay, I would interpret it as a spillover effect. You could also be just sort of some sort of background effect. Because you can see that people who have not joined also raise their savings rate, right? Right. In the case where, in this case, it's actually even for people who have not been saving, they actually even save 1.55%. So it's possible to spill over, right? You see that your friends are saving, so you decide that it's also important for you to save. It also could be some background noise though, so it's possible. It does. Well, the control group has much lower increase, so that partially that reduce the chance that this is actually just noise. Right? It seems like there might be actually some spillover going on here. Right? So this is considered probably the most successful experiment in this fund. Right? Actually running a real commitment device for saving retirement saving, and it actually worked for some people. It's not easy to run this kind of experiment. Now, for Thaler, right? Thaler is famous for the concept of nudge, right? Is that he actually has a book called Nudge. This book kind of saying that, well, it's very often associated with what called libertarian parentalism. Basically, it says that government has to make policy. You can, and like the policy, and given that we know people have this sort of behavioral biases, your policy should be formulated in a way that nudge them towards making the right choice. Right? So this you can also take as evidence to support perhaps mandatory savings, right? Retirement savings. Right? Some people actually want. There are some people actually cannot save enough themselves. Right. Right. So that's the most famous experiment. Here's a completely different type of experiment. This is a study by psychologist, very famous psychologist, Dan Ariely. So he works on a lot of these. He's a psychologist, but he works on all these topics that would be in the field of behavioral economics. So he has this paper, Procrastination, Deadlines, and Performance, Self-Control by Pre-Commitment, which is a study he conducted in his class. 99 students in the class were required to write 3 papers. 51 students were allowed to pick the deadlines for their own paper, 1% late penalty for each day, right? So you can decide when you want to submit your paper. If you were late, then there will be a 1% penalty on the score every day. So if you're time consistent, what deadline should you set?
Average.
If you're time consistent, what will you do? Let's just say, so if you're time consistent, that means you're perfectly rational, you have you have control over your own action, you can do what you say. Then what deadline should you set?
Or at the end.
Or at the end, that's right? Because now, while you might have your perfect self-control, you do not know whether there's any random events that could happen, right, in your life, right? So the rational thing to do is actually to set all deadlines at the very end. Okay, but do people do that? Well, do people do that? Well, let's take a look at the deadlines, right? These are the distribution of deadlines. Black is the first paper. The shaded one is the second paper. White is the third paper. Do people set them all at the end? Well, there are about 10, I guess, 10 students of 13 students actually set the deadline for the first paper at the very end, right? But you can see that that means that there are 30 something students who set the deadlines earlier, right? And you can see that the deadline for the first paper is most of them are roughly in the first like 3 to 5 weeks. The deadline for the second paper is roughly the 8th week, and the deadline for the last paper is around 12 to 14 weeks, right? So your initial reaction is actually what people do, right? Your instinct is what people do. We should set the deadline spaced evenly, right? They're kind of that's what people do. 48 students were given evenly spaced deadlines, no choice, right? Just forced deadlines. My guess is they probably the 99 students. I'm not sure they're actually in the same class. Like it's kind of weird. Like some of your classmates get to set their own deadlines, and you are being forced on a deadline. Maybe they have different sessions in the class, right? I just can't imagine doing that in a class. Like telling half the class, you know what? If you sit on the left-hand side, you can submit the paper anytime you want. If you sit on the right-hand side, sorry folks, you have to submit it like in 3 weeks. Like, but you know what? It's for your own good. Right? Okay, so self-imposed deadlines are significantly earlier than the last date of class. The thing is, the group will evenly spaced deadline being forced on actually have higher grades, suggesting that students in the first group were not setting deadlines optimally. At least that's like what the authors interpret. So you know what? You have unfortunately, you just need deadlines, right? Forced onto you. I think that actually makes a lot of sense. I think that actually makes a lot of sense. I'm supervising STO second year STOT this year. There's some students who just never come to meet me, right? Despite if you don't come, how are you supposed to write a good paper, right? But there are just students who never come, right? So I think they're probably going to do better if I force them to come, right? Which now brings in when at this point we're going to go to the topic of whether how frequent should I force you to come, right? Right? Because there are courses which you have to do presentations every single week, right? So this paper has 2 experiments. The second experiment is this one. 60 students, 60 students were paid to proofread an article, artificially generated article. So it doesn't actually mean anything. The article is artificially generated. So 1/3 has evenly spaced deadline, 1/3 has self-imposed deadline, 1/3 has a single deadline at the very end of the experiment, $1 late penalty for each day. So you are paid for picking up mistakes. You are punished for submitting late. And once again, look, black bar, evenly spaced deadlines. Highest error detected, highest earnings, lowest delay. White bar, self-imposed, everything comes second. Deadline at the very end comes last in everything. You earn less, you submit late, and you do very poor, and you performance is poor, right? So once again, the evidence seems to suggest that students are very bad at actually doing things on time, right? You can guess probably what happens is that they rush. When you just have one deadline at the end, people just rush or everything at the very end, right? Which is also what I think is going to happen with STOT papers. So knowing that now, you probably want to start working on your term paper early. All right, so once again, we come to neural evidence, right? MRI. So, yeah. What about looking at the people's brain? Take a look at the blood flow and see whether there any evidence that what part of brains are involved, what part of your brain is actually involved in making temporal decisions, right? So what this study does is they're going to ask subjects to make choices between two rewards with different delays. And obviously they're going to ask them to do that while lying inside an MRI machine. Okay, so this is what you see. This study by so who did this study? McClure is not as famous, but Lowenstein. Lowenstein is a Carnegie Mellon professor who is a psychologist, but he works on a lot on behavioral economics. So he's a psychologist. David Leibson is the Harvard economist that first came up with this beta delta model in 1994. So what they did, they ran this. So they put subjects into the fMRI machine. Take a look what part of the brains actually light up, right, when they make this temporal decisions. So, okay, so several regions of the brain are especially active when the reward is immediate. So there are several areas that light up, and well, basically, they're looking at. So now the way it works is this, right? They ask them to make choices either is between trade-off between today, 2 weeks, or 1 month, right? So the delay is longer and longer, right? And this, you can see that these area, BSDLO, right? MOFC, PCC, there are several of these regions. The blood flow to these regions are much higher than the blood flow are much higher in the case when you're making an immediate choice than when the choice involves delay. Right? So you can see, so the red is today, right? Red is today. It's the highest in these regions. The bars are confidence intervals, so they are actually statistically significant difference, right? So these regions, a lot of blood flow when there's an immediate trade-off. There are other regions in the brain which have increased the blood flow regardless of the delay. So that's these regions, right? BTs, BCTX, MPA, blah blah blah. So these have indicated where these regions are, and the blood flow is pretty much consistent regardless of the delay. So what the authors interpret is that it seems like when making temporal decisions, humans use two sets of your brain, so two sets of regions in your brain. One set of regions concerns with immediate trade-offs. Another set of regions seems to be concerned with delayed trade-off, right? So because you have these two systems, that might be the reason why you have this inconsistency, right? When you are dealing with immediate trade-off, you have this region in the previous slide that gives you very strong signal. But if you are talking about future trade-offs, then you have the other part of brain that's involved and not so much about the previous part, right? So I think it's not surprising that they have this conclusion because Leibson is involved in this paper, right? Leibson is the co-author, and he is the one who proposed the beta delta model. So obviously, he is very interested in in putting the results in flavor of his model, right? So so this paper interprets that, saying that, well, you know what, the beta delta model actually makes a lot of sense because it's kind of like a now versus future thing, right? And look at the brain. Like there's this set of brain regions which lights up when you're making an immediate decision. There are other regions which lights up regardless of duration. So it seems like there is actually two parts.
So this part refers to which part?
This part is the delta part. This is the delta part if you interpret it, because it's consistently involved regardless of the delay. The previous one would be the beta part because it only lights up when you're making immediate trade-offs, right? So that's what they interpret, right? These type of papers typically goes to either science or nature, right? Because it's cross-disciplinary kind of like study. So right. So so if you come so uh, if you compare the rate of change relative to their baseline in those areas, so see this paper actually literally used this diagram is copied from the paper, right? So they literally use beta areas and delta areas in the description. So if you measure the change in blood flow relative to the baseline, it looks like um, in an immediate choice, the beta area, so the area which the area in the first slides, have a much bigger relative change relative to normal, right? So it's much higher. When it's talking about choices that is delayed, then the delta areas in the second slide have higher relative change in blood flow relative to the normal times. Right? So they're saying that when you're making choice immediate trade-off, the beta regions are having a lot of blood flow, so that's what it dominates the decision. In you're making choices that involves trade-off in the future, it's mostly these delta areas that have increased blood flow. The beta areas is pretty much not responding much, so your decision is dominated by this part.
I thought delta is not consistent over time.
Yeah, so delta is the exponential discounting part, right? The consistent part that governs all time periods. The beta part is governs the discounting of all future versus today. Right? So this part is about future versus today. This is about any two adjacent periods. Right? So that's their interpretation, right? That's that's their interpretation that in making immediate trade-offs, one region dominates. In making delayed trade-offs, another region of your brain dominates. Other regions of your brain dominates. So that's why they're different behavior. So this would be evidence in support of actually a model like beta delta, where you have this unique separation. So now you might object to their findings, right? Because who knows what those areas in the brain actually does, right? How do you know what they actually do? Maybe it's actually lighting up because those areas are involved in processing information. How do you know? You don't actually know, right? So what they do is they try to rule out this factor by varying the difficulty of the task. So they make the difference in reward smaller, right? So they make if the difference in reward is very large, supposedly the task is simple, right? If I'm telling, okay, you can get 100 today or 1 million next week, then it's an easy task. You probably don't even need to think about it, right? But if it's 100 today and $103, then maybe you have to think about it, right? Okay, well, maybe the amount is too small, but something like 1 million today and $1,030,000 next week, right? You might have to think about it because $30,000 is not a small amount, so you might have to want to think about it, that kind of stuff. So that's what they did. They tried to make the reward smaller to make the task more difficult, because presumably when the reward is small, people have to think about it. And it seems like let's see. I actually don't quite remember what this is. This is an easy decision. All right. So there is some change in the blood flow relative when the task becomes more difficult. Right. So once again, this would be the confidence interval, right? So it seems to be significantly different. So if these regions are purely involved in fish, let's say fish processing facial information, it should not depend. The blood flow should not depend on the difficulty of the task, right? Like I'm showing you some numbers on the screen. Your brain lights up because you're processing the screen. So no matter what I show you on the screen, your brain should light up the same amount. But now we see that your brain lights up more when the task is difficult. That suggests the regions are not just involved in like visually processing information, but actually involves in making decision. Right? That's what they try to do. Right. So okay. So that's the, okay. So we have already seen evidence of future bias, right? Where people say they are really actually they're very patient. There's some experiments that actually show people can be very patient, very future bias. Now, what I want to talk about is alternative theories. As I said, this the reason behind time inconsistency is not settled. For example, let's take a look at this case, right? Suppose your friend tells you that earlier that she does not want to eat ice cream, but now when she's in front of an ice cream, she eats it. How do you explain this behavior?
Unable to resist.
All right. So now there are multiple possibilities here. What do you mean by unable to resist?
She has a weak willpower.
Right. So it's about like willpower, right? You have that when an ice cream is in front of you, you suddenly just do not have the ability to resist, right? That's a different model than hyperbolic discounting, right? Now, if it's about hyperbolic discounting, you can try to explain this with hyperbolic discounting. Hyperbolic discounting would say, you don't want to eat ice cream because ice cream is bad for your health, or perhaps it makes you fat, right? So eating the ice cream now is happy, but the cost is delayed, right? So if you're rational, you don't want to eat ice cream, but when the ice cream is in front of you, the benefit is immediate and the fatness is in the future, so you don't care, right? That's the hyperbolic discounting explanation for eating the ice cream, even though you say you don't want to do so. But now you have an alternative explanation, which is to say it's about willpower. People cannot resist the item when it's in front of them. That's a completely different model. At least conceptual, it's a completely different model. Yeah. So this type of model is called temptation utility. So your utility function essentially depends on your choice set, right? When ice cream is not in your choice set, you can say whatever you want, right? But when ice cream actually enters your choice set, it changes your utility in a way such that you would actually consume the ice cream. Here's another from the perspective of psychology, another possibility is that you simply are not thinking rationally. When you see an ice cream, you blank out, right? And then when you wake up, you just have eaten the ice cream already. That's called basically what I call Q theory or two self model, right? You have where humans, right? This is a very common theory, a very popular theory in psychology. Your mind works in your mind has two self. One is a rational one. One is a kind of an impulse one. So when you see an ice cream, the impulse you take over and you decide to consume the ice cream. This is also kind of what Daniel Kahneman's book Thinking Fast and Slow talking about. Slow is the rational part. Fast is the impulse part of your brain. Right? So you're not even thinking, you just eat the ice cream. Now you might ask what's different? Is there really such a big difference between these type of models? Well, conceptually, yes. Mathematically, sometimes. The temptation utility model is it's kind of very, I'll say, very classical. The thing is, this model is the author want an axiomatic foundation. So supposing this you can say is a rational model. It's rational. It's that your utility change with the choice set. Right? It's all rational. You're not you're just simply your utility change with choice set. So the authors in this paper, they are actually professors in Princeton University. They really emphasize this difference, is that their model is rational, whereas the beta delta model, the hyperbolic discounting, is not rational in their belief, right? Because in hyperbolic discounting, your behavior change kind of against your view, right? You want to not eat the ice cream. When the ice cream comes, when in the future period your preference change. So you you're doing something against your previous view. This case, they emphasize this is rational. Your utility change with the choice set. So it's rational that you change your choice, right? Now I think a lot of difference is conceptual. I mean, in terms of the actual implication is not that different very often. Okay, here you go.
All right, buddy. Here's the deal. You're gonna help me with a little experiment, okay? Okay. This is a hard cookie. It's your cookie. You can eat it now if you want, but I'm gonna leave it for a little bit. When I come back, if you haven't eaten it, I'll give you another cookie. But if you do eat it, that's all you get. Okay? Okay, your choice. You can eat it if you want to, but if you wait, when I come back, if you didn't eat the cookie, I'm gonna give you 2 cookies. You understand?
Yes.
All right. You eat the cookie?
Baby, I like cookies.
How'd you do? You eat it?
No.
No. What did you eat?
You don't want 2 cookies?
Yeah, that's awesome. Well, you did it. You got 2 cookies. All for you. Awesome, huh? Cool, good job.
All right. So now Why are psychologists so fascinated with these studies? As I said, this study, the earliest of these studies, is one that's called a marshmallow experiment, which basically is the same experiment done with marshmallows, right? If you wait, you get more marshmallows. Now, why are psychologists so fascinated with this study? Is that in the marshmallow experiments, they actually did a follow-up, and the authors claim that when the kids grew up, those who resist eating the marshmallow immediately actually have better life outcome. So that's why psychologists became so fascinated with these studies, because it seems like it makes sense, right? Like your ability to delay gratification when you were young would actually be predictable of your future achievement. Now, subsequent studies have actually lower the estimate of the effect by a bit. It seems like the effect is actually not that strong. Okay, now I'm going to ask you, why do you think this the interpretation that the ability to resist gratification when you were young would actually what is hypothesis that your ability to resist gratification when you were young is predictive of your future achievement might not actually be as strong as we might think. Right? What would be an alternative explanation to now? Given that you observe kids that resist eating the cookie or the marshmallow do go on to have a better life, right? Let's just say that's a fact. You observe that. What might be alternative explanation? Think about it. Now, the authors of the original marshmallow study, they interpret it as saying your ability to resist gratification is the force behind. So that ability is valuable. It makes you more it makes you more achieving in the future. That's the interpretation. But that might not be the correct interpretation. So what would be an alternative interpretation? Think. Like now it has so what would you now given that all you know is that the kid so you have kids that can resist gratification and there are kids who cannot. Try to make some educated guess about what characteristics the kids would have that make that difference.
In their brain, their beta will be less.
But essentially, that's kind of still saying about your ability to resist. Well, I mean, it might not call it gratification. It might be just your ability to resist procrastination. But it's still saying that you have some better ability here.
Family background.
Family background. What do you think? Family background.
If your parents are educated or if they're richer, they might teach you that you have to delay.
Okay. So family background is something that the original authors did not consider. Now, I actually have even simpler explanation than yours. If my family is rich, I have plenty of cookies at home. I'm already like packed with cookies every single day, right? Why would I? Yeah. Right. Why would I crave for one single cookie? Right. So the reason why subsequent studies have found the effect to be much smaller is because the subsequent studies control for family background. Once you control for family background, for whatever reason, it could be because of family teaching, could be because the fact that they are richer, right? It actually makes the findings of study much weaker than previously thought. Another thing you want to think about is it really irrational to eat the cookie? I mean, it might not even be about gratification. It might not be about gratification. It's not clear what is happening in the kid's mind when they are in the study, right? Because you can see from the instruction there seems to be no indication of how long they have to wait, right? Like you could have very different expectation of how long you have to wait, right? Right? I mean, maybe I think maybe I think the wait is actually quite short, so I would be willing to wait, right? Okay, wait for 2 minutes, another cookie, fine. But maybe another kid would have thought that it's going to be like 10-minute wait, and it's not worthwhile, right? So without knowing more details, and I think a lot of these studies is actually as recorded, they don't actually tell the kids how long they have to wait, right? So the kids might think that they have to wait very long, and they don't want to. Yeah. So yeah, they don't. Yeah, actually, that's very good. That's actually a paper, I think, a psychology paper somewhere last year or something, that suggests that, well, if you believe that the delay is going to be getting longer, the rational thing to do is actually consume the cookie immediately, right? Because we think that, well, okay, he might not be coming back at all. Why wait, right? So yeah, so there are a lot of things you have to consider. Which is, well, the nice thing about science, right? Okay. I mean, in general, you have a new hypothesis, you can test it out and see it actually refutes previous findings, right? Okay, so that's all for today. Next week we're going to do 2 more examples on time inconsistency, right? Mathematical examples, right? Workbook, and then yeah, we'll see what we're going to do next then. Because the slides that I've uploaded only last to this topic. So I have to think about what we're going to talk about next week and beyond.